-7.6%. That was the average annual return of the Japanese stock market from 1989 to 2009, 20 years of losses. But here's the part that surprises people. During those same 20 years, the market had positive returns in 11 of them, more up years than down years. So how can you have more winning years than losing years and still lose money? The answer is hidden in one word: average. The problem is that most people think of average as the arithmetic mean. Add up all the returns, divide by the number of years. But when you are dealing with investment returns, the arithmetic mean lies to you. It tells you what the typical single year looked like. It does not tell you what actually happened to your money. For that, you need the geometric mean. And the difference between these two averages is not academic. It is the difference between thinking you made money and discovering you lost it. Statistical concepts in market returns. Lesson 4 of CFA Level 1 Quantitative Methods. Here is everything you will master in this lesson. The 4 types of mean and when to use each one: arithmetic, geometric, harmonic, and weighted; median and mode, and when they beat the mean; measures of dispersion, range, mean absolute deviation, variance, and standard deviation; coefficient of variation, the tool that lets you compare risk across completely different investments; skewness and kurtosis, the 2 properties that tell you whether the normal distribution is safe to use; and 5 exam questions with full solutions. This is the lesson where numbers start telling stories. Part 1. Measures of central tendency. Where is the center of your data? The arithmetic mean. You already know this one. Add up all the values and divide by how many there are. X bar equals the sum of all xi values divided by n. Think of it as the balance point. If you put all your data points on a seesaw, the arithmetic mean is where you place the fulcrum to make it balance perfectly. For investment returns, the arithmetic mean answers this question: if I pick one year at random from this dataset, what return should I expect? It is the best estimate of next year's return if the returns are independent from year to year. Let us work through a concrete example. A stock has 5 annual returns: 15%, minus 10%, 20%, minus 5%, and 12%. Step 1. Add them all up. 15 minus 10 plus 20 minus 5 plus 12 equals 32. Step 2. Divide by the number of years. 32 divided by 5 equals 6.4%. The arithmetic mean return is 6.4%. This means if you had to guess next year's return with no other information, 6.4% is your best single estimate. Now the geometric mean. This is the one that actually matters for your portfolio. The geometric mean return equals the nth root of the product of 1 plus each return minus 1. In plain language, you multiply all the growth factors together, then take the nth root to find the single constant growth rate that would produce the same final result. Why is this different from the arithmetic mean? Because returns compound. If you lose 50% and then gain 50%, the arithmetic mean says 0. You lost 50, you gained 50, average is 0. Sounds like you broke even. But you did not break even. You started with $100, lost 50, had $50 left, then gained 50% of 50, which is 25. You ended with $75. You lost 25%. The geometric mean captures this. The arithmetic mean misses it completely. Same 5 returns: 15%, minus 10, 20, minus 5, 12. Step 1. Convert each return to a growth factor by adding one: 1.15, 0.9, 1.2, 0.95, 1.12. Step 2. Multiply all 5 together. 1.15 times 0.9 times 1.2 times 0.95 times 1.12 equals 1.3206. Step 3. Take the 5th root. 1.3206 raised to the power 1/5 equals 1.0572. Step 4. Subtract 1. 0.0572, which is 5.72%. Notice the geometric mean, 5.72, is lower than the arithmetic mean, 6.4. This is always true when returns vary. The geometric mean is always less than or equal to the arithmetic mean. The gap between them increases as volatility increases. This relationship is tested on the exam. Let us see the difference in dollar terms over those 5 years. If you invested $10,000 at the arithmetic mean of 6.4% constant for 5 years, you would have $13,649. If you invested $10,000 and experienced the actual 5 returns, you would have $13,206. That difference of $443 is the cost of volatility. The geometric mean of 5.72% correctly predicts the 13,206 number. The arithmetic mean overshoots by $443. Exam rule. Use arithmetic mean for estimating a single future period return. Use geometric mean for measuring actual historical compound growth. The harmonic mean. This is the least intuitive of the 4 means, but it has one very specific use case on the exam. The harmonic mean equals n divided by the sum of the reciprocals of each value. In plain language, you flip each number upside down, average those, then flip the result upside down again. When do you use this? Dollar cost averaging. When you invest a fixed dollar amount at regular intervals, like $1,000 per month into an index fund, the harmonic mean gives you the true average cost per share, not the arithmetic average of the prices, the actual cost you paid. You invest $1,000 per month into a stock for 3 months. Month 1, the price is $50 per share. You buy 20 shares. Month 2, the price drops to $40. You buy 25 shares. Month 3, the price rises to $60. You buy 16.67 shares. Total invested, $3,000. Total shares, 61.67. Your actual average cost per share, 3,000 divided by 61.67 equals $48.65. The arithmetic mean of the 3 prices is 50, but you did not pay 50, you paid $48.65. The harmonic mean gives you that correct number. 3 divided by 1 over 50 plus 1 over 40 plus 1 over 60 equals $48.65. Exam pattern. Whenever you see fixed dollar investments at varying prices, the answer is the harmonic mean. The weighted mean. Sometimes, not all observations are equally important. The weighted mean equals the sum of each weight times its corresponding value. The weights must add up to 1 or 100%. You use this constantly in finance. A portfolio return is a weighted mean. If you have 60% in stocks returning 10% and 40% in bonds returning 4%, your portfolio return is 0.6 times 10 plus 0.4 times 4, which equals 7.6%. On the exam, weighted means appear in portfolio returns, expected values and probability, and GDP-weighted economic indicators. Median and mode. 2 simpler measures that sometimes outperform the mean. The median is the middle value when you sort data from smallest to largest. If you have an odd number of observations, it is the exact middle one. If even, it is the average of the 2 middle values. The median's superpower is that it ignores outliers. If 5 portfolio managers earned returns of 8, 9, 10, 11, and 90%, the mean is 25.6, but the median is 10. The median tells you what the typical manager earned. The mean is distorted by that 190% outlier. The mode is simply the most frequent value. In a return distribution, the mode tells you the most likely single outcome. A distribution can have 1 mode, unimodal, 2 modes, bimodal, or more than 2, multimodal. Part 2. Measures of dispersion. Central tendency tells you where the center is. Dispersion tells you how spread out the data is around that center. And in finance, dispersion is risk. The range. The simplest measure of dispersion, maximum value minus minimum value. If the highest annual return was 30% and the lowest was minus 20%, the range is 50 percentage points. The range is easy to calculate but deeply flawed. It uses only 2 data points, the highest and lowest. A single outlier can make the range enormous even if every other value is tightly clustered. Think of it like judging a city's temperature by looking only at the hottest day and the coldest day. You know the extremes, but nothing about what a typical day feels like. Mean absolute deviation, or MAD. This measures the average distance of each data point from the mean. For each value, you calculate how far it is from the mean, take the absolute value so negatives do not cancel out positives, then average all those distances. MAD equals the sum of the absolute values of xi minus x bar divided by n. The key phrase is absolute value. Without it, the positive deviations and negative deviations would sum to 0 every single time. That is mathematically guaranteed. So MAD forces them all positive before averaging. MAD is intuitive. It literally answers the question, on average, how far is each observation from the mean? Variance. Instead of taking the absolute value to handle negative deviations, variance squares them. Population variance equals the sum of each xi minus the mean squared divided by n. Why square instead of taking absolute values? Two reasons. First, squaring penalizes large deviations more heavily. A deviation of 10 gets a weight of 100, while a deviation of 2 gets only 4. This makes variance more sensitive to outliers. Second, squared values have better mathematical properties. You can decompose variance, add variances of independent variables, and build upon it for regression and portfolio theory. The downside? Variance is in squared units. If your returns are in percent, variance is in percent squared. That is not intuitive, which brings us to standard deviation. Standard deviation. Take the square root of the variance. Now you are back in the original units. If returns are in percent, standard deviation is also in percent. Sigma equals the square root of sigma squared. Standard deviation is the measure of risk in finance. When someone says a stock has volatility of 20%, they mean the annualized standard deviation of returns is 20%. Higher standard deviation means wider dispersion of returns around the mean, more uncertainty, more risk. For a normal distribution, about 68% of observations fall within one standard deviation of the mean, about 95% fall within 2, and 99.7% within 3. This is the 68, 95, 99.7 rule. Memorize it for the exam. Critical exam distinction. Population variance divides by n. Sample variance divides by n minus 1. Why the difference? When you calculate variance from a sample, you use the sample mean as an estimate of the true population mean. That sample mean is calculated from the same data. This introduces a bias. The sample will always appear less spread out than the true population because the sample mean is positioned to minimize deviations within the sample. Dividing by n minus 1 corrects for this bias. N minus 1 is called the degrees of freedom. You had n independent pieces of information, but you used one of them to estimate the mean, leaving n minus 1 for estimating the spread. Exam rule. If they say population, divide by n. If they say sample, divide by n minus 1. If they do not specify and the data is a subset of something larger, assume sample, divide by n minus 1. Let us calculate standard deviation for our 5 returns. 15 minus 10, 20 minus 5, 12. The mean is 6.4. Step 1. Subtract the mean from each value. 15 minus 6.4 is 8.6. Minus 10 minus 6.4 is minus 16.4. 20 minus 6.4 is 13.6. Minus 5 minus 6.4 is minus 11.4. 12 minus 6.4 is 5.6. Step 2. Square each deviation. 73.96, 268.96, 184.96, 129.96, 31.36. Step 3. Sum the squares. 689.2. Step 4. Assuming this is a sample, divide by n minus 1, which is 4. That gives 172.3. This is the sample variance. Step 5. Take the square root. 13.13%. A standard deviation of 13% tells you, in a typical year, the return deviated about 13 percentage points from the average. That is substantial risk. Tot 3. Coefficient of variation, the tool that lets you compare apples to oranges. Here is the problem. Stock A has a standard deviation of 20% and a mean return of 15%. Stock B has a standard deviation of 10% and a mean return of 5%. Which one is riskier? If you look only at standard deviation, A is riskier, 20 beats 10. But that is misleading. A also has a much higher return. 20% volatility on a 15% return is very different from 10% volatility on a 5% return. The coefficient of variation, or CV, solves this by measuring risk PER unit of return. CV equals the standard deviation divided by the mean. Stock A, 20 divided by 15 is 1.33. Stock B, 10 divided by 5 is 2.00. Stock B has more risk per unit of return. Higher CV means relatively more risk. Lower CV is preferred. The exam loves this comparison. Let us see this side by side. Stock A, standard deviation 20%, mean return 15%. CV is 1.33. Stock B, standard deviation 10%, mean return 5%. CV is 2.00. Even though Stock B has half the absolute risk, it has 50% more relative risk. For every percentage point of return you earn from Stock B, you are taking on more risk than you do with Stock A. This is exactly the kind of question where candidates pick the wrong answer because they only look at standard deviation. Part 4. Skewness. When your data leans to one side. A normal distribution is perfectly symmetric. The mean, median, and mode are all the same value, right in the center. But real-world return distributions are almost never perfectly symmetric. They are skewed. Positive skew means the right tail is longer. There are a few very large positive returns pulling the mean above the median. Negative skew means the left tail is longer. There are a few very large negative returns pulling the mean below the median. Here is the critical relationship for the exam. For a positively skewed distribution, mode is less than median, which is less than mean. The mean gets pulled toward the long right tail. For a negatively skewed distribution, mean is less than median, which is less than mode. The mean gets pulled toward the long left tail. Memory trick. The mean is always pulled toward the tail. Always. The mode stays at the peak. The median is in between. Why does skewness matter for investors? Most equity return distributions show slight negative skew. That means the left tail, the tail of large losses, is fatter than a normal distribution would predict. In practical terms, crashes are more common and more severe than a symmetric bell curve would suggest. If you use a normal distribution to model returns and the actual distribution is negatively skewed, you will underestimate the probability of large losses. This is exactly what happened in 2008. Risk models assumed normal distributions. The actual distribution had significant negative skew and fat tails. The model said a loss that large was a once in 10,000 year event. The market said otherwise. Exam implication. When a return distribution is negatively skewed, the standard deviation understates the true downside risk. You need to know this. Type 5. 5. Kurtosis. How fat are the tails? Kurtosis measures the thickness of the tails and the peakness of a distribution. A normal distribution has a kurtosis of 3. This is the benchmark. Excess kurtosis equals kurtosis minus 3. A normal distribution has excess kurtosis of 0. There are 3 categories. Leptokurtic. Excess kurtosis greater than 0. Fatter tails than normal, more peaked in the center, more extreme outcomes, both large gains and large losses, than a normal distribution would predict. Platykurtic. Excess kurtosis less than 0. Thinner tails, flatter peak, fewer extreme outcomes. Mesokurtic. Excess kurtosis equal to 0. This is the normal distribution. For the exam, remember lepto means more. Leptokurtic means more peak, more tail, more risk of extreme events. Most financial return distributions are leptokurtic. Fat tails. This means extreme returns, both positive and negative, happen more often than the normal distribution predicts. Combining skewness and kurtosis gives you the full picture. If a return distribution has negative skew and positive excess kurtosis, that is the worst combination for a risk manager. Negative skew means the crash tail is longer. Positive excess kurtosis means both tails are fatter. Together, they mean large losses are more likely and more severe than a normal distribution predicts. This is the exact profile of most equity markets. When you see an exam question that asks about the limitations of using standard deviation alone as a risk measure, the answer is skewness and kurtosis. Standard deviation treats upside and downside symmetrically. Skewness shows they are not symmetric. Kurtosis shows the probability of extreme events is wrong under normal assumptions. Part 6. Exam questions. 5 questions. Full solutions. Every wrong answer explained. Question 1. A stock has annual returns of positive 50% and negative 50% over 2 years. The geometric mean annual return is closest to A. 0%, B. minus 13.4%, C. minus 25%. Pause and try it. If you chose A, you calculated the arithmetic mean. 50 plus negative 50 divided by 2 equals 0. That is the trap. The correct answer is B. The growth factors are 1.5 and 0.5. Multiply them, 0.75. Take the square root, 0.866. Subtract 1, minus 0.134, or minus 13.4%. Why not C? Minus 25% would be the total loss divided by 2 years linearly, but that ignores compounding. The geometric mean correctly accounts for the multiplicative nature of returns. Question 2. An investor puts $1,000 per month into a fund. The share price is $10 in month 1, $8 in month 2, and $12 in month 3. The average cost per share is closest to A. $10, B. $9.73, C. $9.23. Try it. If you chose A, you took the arithmetic mean of the prices. 10 plus 8 plus 12 divided by 3 is 10. That is wrong for dollar cost averaging. The correct answer is B. Shares bought 100 plus 100, 25 plus 83.33 equals 308.33. Total invested 3,000. Average cost 3,000 divided by 308.33 equals $9.73. This is the harmonic mean. 3 divided by the quantity 1 over 10 plus 1 over 8 plus 1 over 12, which equals 973. C is too low. A common mistake is dividing total invested by total months instead of total shares. Question 3. Fund A has a mean return of 12% and standard deviation of 18%. Fund B has a mean return of 8% and standard deviation of 10%. Based on the coefficient of variation, which fund has less risk per unit of return? A, Fund A, B, Fund B. See they are equal. Calculate it. Fund CV is 18 divided by 12, which is 1.50. Fund B CV is 10 divided by 8, which is 1.25. Fund B has a lower CV, meaning less risk per unit of return. The correct answer is B. If you chose A, you compared standard deviations directly. Fund A has higher absolute risk but also much higher return. CV adjusts for this. This is a classic exam trap. Many candidates see the higher standard deviation and immediately choose A as riskier. But CV tells the real story. Question 4. A return distribution has a mean of 7%, a median of 8%, and a mode of 9%. This distribution is most likely A. Positively skewed, B. Negatively skewed, C. Symmetric. Think about it. The correct answer is B. Negatively skewed. Here is why. Mean is less than median, which is less than mode. 7, 8, 9. The mean has been pulled to the left, toward the long left tail. If you chose A, you have the relationship backwards. In positive skew, mean is the largest, not the smallest. Mode is less than median is less than mean. If you chose C, remember that symmetric means all three are equal. The memory trick again. The mean always chases the tail. If the mean is pulled left, there is a left tail, which means negative skew. Question 5. Compared to a normal distribution, a leptokurtic distribution has A. A flatter peak and thinner tails, B. A higher peak and fatter tails, C. The same peak with fatter tails only. Recall the definition. The correct answer is B. Leptokurtic means excess kurtosis greater than 0. Compared to the normal distribution, it has more concentration around the mean, creating a higher peak, and more probability in the tails, creating fat tails. If you chose A, you described platykurtic. Platy means flat. Platykurtic has a flatter peak and thinner tails. If you chose C, that is partially correct about the tails, but wrong about the peak. Leptokurtic distributions have both a higher peak and fatter tails. The probability mass comes from the shoulders of the distribution, which are thinner than normal. Exam pattern. Lepto equals more peak, more tail. Platy equals less peak, less tail. Let us go back to where we started. The Japanese stock market, negative 7.6% annualized over 20 years, despite having more positive years than negative ones. Now you understand why. The arithmetic mean of those annual returns was actually positive. If you just added up returns and divided by 20, it looked okay. But the geometric mean told the truth. The compounding of those large negative years, especially the crash of 90% from the 1989 peak, destroyed wealth in a way the arithmetic mean could not capture. And the distribution was negatively skewed with high kurtosis. The losses were not just frequent, they were extreme. One number cannot tell this story. You need the full statistical toolkit: mean, median, standard deviation, skewness, kurtosis. Together, they give you the complete picture. Your cheat sheet. Save this. Arithmetic mean, sum divided by n. Best for estimating a single future return. Geometric mean, nth root of the product of growth factors, minus 1. Best for measuring actual compound growth. Always less than arithmetic when returns vary. Harmonic mean, n, divided by sum of reciprocals. Used for dollar cost averaging. Weighted mean, sum of weight times value. Used for portfolio returns. Range, max minus min. Simple but flawed. MAD, average absolute deviation from mean. Variance, average squared deviation. Population divides by n, sample by n minus 1. Standard deviation, square root of variance. The measure of risk. CV, standard deviation divided by mean. Compares risk across different investments. Lower is better. Positive skew, mode less than median, less than mean. Negative skew, reverse. Leptokurtic, fat tails, high peak, excess kurtosis greater than 0. In the next lesson, we tackle probability concepts, the foundation of everything from option pricing to portfolio theory. Subscribe and hit the bell so you do not miss it. If this video helped you, leave a like. It takes 2 seconds and it tells YouTube to show this to other CFA candidates who need it. See you in Lesson 5.